Welcome back to the course on software-defined networking. In this lesson, we'll be wrapping up our discussion of the history of software-defined networking, and in particular, we will explore the history of control of packet switch networks. We've already explored a little bit the history of central network control, but most of that was in the context of the phone network and circuit switch networks. And today, we'll look at how the control of packet switch networks has evolved. I'll begin by reminding us why separating network control from the data plane is a good idea, and then we'll look at different ways that have been developed to control packet switch networks. We'll start by looking at the Forces protocol, which was developed in the Internet Engineering Task Force, which effectively defined a custom separate control channel to control switches or forwarding elements. Then we'll look at the routing control platform, which used an existing protocol, in particular the Border Gateway Protocol, to dictate or control the routing decisions or forwarding decisions that BGP-speaking routers in a backbone network made. Then we'll look at how the emergence of open hardware enabled the much more widespread adoption of separate control of packet switch networks. So first, let's remind ourselves why separate control is a good idea. First, it enables more rapid innovation since control logic isn't directly tied to the hardware. Second, it enables the controller to potentially see a network-wide view, thereby making it easier to infer and reason about network behavior. Finally, having a separate control channel makes it possible to have a separate software controller which facilitates the introduction of new services into the network much more easily. Let's now look at three different ways that were developed to control packet switch networks. The first instance of a separate control channel for packet switch networks came out of the Internet Engineering Task Force in the form of the Forces protocol. The protocol was first standardized in 2003, and there were three implementations of this particular standard. The standard essentially defined protocols that would allow multiple control elements to control forwarding elements, which would essentially be responsible for forwarding packets, metering, shaping, performing traffic classification, and so forth. So the idea was that these switches or forwarding elements could be controlled over a standard control channel called the Forces interface. And there might be multiple such controllers controlling the forwarding behavior of these forwarding elements. So this was all well and good, and in some ways it looks a lot like the OpenFlow standard that we know today. But the problem with this particular approach was that it required standardization, adoption by vendors, and deployment of new hardware. And these particular hurdles were the same hurdles that were the motivation for some of the earlier work, such as the active networks projects that we looked at. Another approach was to essentially use existing protocols as control channels, essentially hijacking existing routing protocols to send control messages to the forwarding elements. This approach was taken by the routing control platform. The idea was that every autonomous system or independently operated network might have a routing control platform, or an RCP, which would compute routes on behalf of the routers and then use the existing BGP protocols to communicate these routes to the routers. So the idea was that computation would happen up here in the RCP, but once the routes were computed, the results of that computation would be pushed into the router's forwarding tables by standard routing protocols. So these routers would be under the impression they were just speaking to any old router, but in fact they were speaking to a smart box that was actually computing the routes on their behalf. Using these existing in-band protocols to control a packet switch network effectively makes it easier to transition from the status quo to something where all of the control is centralized in a particular network. The RCP effectively used BGP as a control channel so that the forwarding elements thought that they were talking to just another router, but in fact all of the smarts for the network were centralized at a single point. This approach makes deployment somewhat easier since it doesn't require standardization on a new set of control protocols. However, the problem with the approach is that the control that one has over the network is constrained by what existing protocols like BGP can support. So effectively, the RCP was limited because all it could do is control BGP routing decisions, when in fact, a network operator might want to control a much wider range of behaviors. Ultimately, the architecture still proved useful, and a version of the RCP is currently running in at least one large backbone network today to do things like automated traffic redirection for security incidents or traffic scrubbing. But nevertheless, the range of applications that something like the RCP can support is still somewhat relatively limited in comparison to what might be possible with a general separate control plane. Customizing the hardware in the data plane potentially makes it easier to support a much wider range of applications in the control plane. The first project to realize this was the Ethane project, which presented a network architecture for the enterprise which allowed direct enforcement of a single fine-grained network policy at something called a domain controller. That domain controller would compute the flow tables that should be installed in each of the enterprise's switches based on the access control policies defined at the domain controller. Ethane required the deployment of custom switches, and the project implemented several of these based on OpenWRT, NetFPGA, and Linux. The problem with this approach, of course, is that it requires custom switches that support the Ethane protocol. So what we're looking for is something that gets us the best of both worlds, something that could operate on existing protocols yet wouldn't require customizing the hardware. The answer to that question was OpenFlow. And here the idea was to basically take the capabilities of existing hardware and open those up such that a standard control protocol could control the behavior of that hardware. In OpenFlow, a separate controller communicates with the switch's flow table to install forwarding table entries into the switch that control the forwarding behavior of the network. Because most switches already implemented flow tables, the only thing that was necessary to make OpenFlow a reality was to convince the switch vendors to open the interface to those flow tables so that a separate software controller could dictate what would be populated in those flow tables. So what have we learned about network control in this lesson? One of the lessons is that control and data planes should definitely be decoupled, because vertically integrated switches make it very difficult to introduce new control planes. In some sense, Forces looks a lot like OpenFlow, but because it required new standardization and adoption and changes to the hardware, deployment ultimately became very difficult. The second lesson is that using existing protocols makes deployment easier, but it also constrains what can be done, and we saw that in the RCP. Finally, we saw that open hardware can allow decoupling the control and can actually spur adoption. And this is potentially one of the reasons that made OpenFlow so incredibly successful relative to these other similar proposals.